Piezo SHOCK Show, and I'm going to answer the question today. Should an ultrasonic transmitter and receiver be used in phase? So we're going to talk about phase angle, what causes it. But this is not phase angle just in a single transducer. As I'm going to describe, we have, in this case, a transmitter and a receiver. Now, whether this is occurring in water medium or an air medium, it doesn't matter. This relates. Now, if you are choosing a solid medium or elastic medium like steel or so, now sound can reflect multiple times in the material. There's edges. There's a finite space. But when you're talking about transmitting things in air and or in water, reflection surfaces are not plentiful. There's not like a container. Unless you're doing it in a container, then there may be reflections and some other differences that you may encounter. However, we're talking about air and water. Assume it's an infinitely wide medium. Then in those cases, the resonance system is kind of very decoupled from the transducers in a sense. The system is decoupled. So let's continue to talk about transmitting from one transducer and receiving from another. You could also consider this as having a reflector, and the transmitter is also a receiver. Some of this discussion will also apply to that. Okay, now I want to talk about transmitters and receivers. We're going to be a little bit high level. It's not necessarily exactly what's applied in practice due to practical constraints, but I'm going to give you some food for thought here. These are two impedance traces, right? And we have the transmitter TX and a receiver RX. The frequency at which if you're the transmitter will generate the most sound will be at the resonant frequency for a particular voltage drive. If you assume a particular voltage drive, you'll have the most sound, the highest intensity of sound generated, the highest acoustic output power generated from the resonant frequency. That is specifically the mechanical resonance, but right now we're just assuming the mechanical and electrical are the same, pretty much. But on the receiving side, this is where things get interesting. The receiver, assuming it is an open circuit receiver, if you have an open circuit receiver, then you're actually generating the most voltage at that system. An open circuit system is going to resonate at its anti-resonant frequency. Now, depending if you're just receiving the signal, then you pretty much have an open circuit system because you're trying to generate voltage on the outside. However, if you are using that, now some folks are interested in transmitting power through air. If you are actually transmitting power through air and receiving it and converting that back into electricity, now your impedance will be different because you'll have something in between the resonance, which is a perfect short circuit, and the anti-resonance, which is a perfect open circuit. You'll have something in between those two frequencies. But let's just take a look at an example where we want to drive a transmitter at optimum conditions and design the receiver such that to have the maximum output voltage. So if you drive your transmitter at the resonant frequency right here, that delivers a resonance frequency. That delivers the most sound output. And if you actually add, let's say, if you had your same receiver and transmitter topology, but let's say you add a little bit of material like epoxy to reduce the frequency, now you see the receiver frequency went down. That kind of aligned the resonance of the transmitter and the anti-resonance of the receiver. Now, the anti-resonance of the receiver is the open circuit condition. That condition is which you're trying to generate voltage on. I hope that makes sense. So we'll go forward. Now we're going to talk about phase. This is a great discussion. I love this question, actually. So let's say we had this transmitter, and this is shooting out acoustic waves through space, 40 kilohertz, whatever. And how do you calculate wavelength in air? Wavelength. So wavelength is equal to the speed. So it's equal to or the speed of sound. The velocity is meters per second. So that's equal to the wavelength over the frequency. Right? So I explained that in a few videos back. It all works on the units, meters per second, speed of sound. You have to know the speed of sound in air equals the wavelength divided by the frequency. Because wavelength is in terms of meters, frequency or multiplied, sorry, multiplied by frequency, because frequency is 1/seconds. Okay, so oopsie. All right, so you can then determine what we have here is this transmitter shooting out energy in air. Now it's not shooting out in waves. This is longitudinal waves. So there's pressure gradients as you go along. So well, let's assume that you put your transducer, your receiver at x1. You put your receiver at x1. What is going to be the voltage? So right now, if you look at the phase, so if we put our receiver exactly at the same spot, so that we have this upward going curve down and coming back up. If you put it at that spot exactly here, then you should have the exact same waveform. The yellow and the green, the receiver and the transmitter will be the same. The transmitter, I'm just assuming it's yellow and receiver is green. But if we put it right here, you can consider this pressure, or you can consider this velocity, however you want to consider this curve, basically representing, or what's receiving. Probably velocity is not going to be the thing. Probably pressure. We're going to be measuring pressure, so that's going to be the thing we measure. So if this is the pressure, and obviously this is oscillating through time, this wave is propagating. So it's not that. So this is taken at a specific time, because the pressure here is going to be alternating high and low, and this wave is going to be propagating out. So this is a specific incidence in time, but we're just using it to correlate phase, because the phase will always be in sync if they are a wavelength apart. So if you have this and the wave is going down, so you're kind of halfway, 90 degree or 180 degrees out of phase, then you'll have exactly 180 degrees out of phase measure, 180 degrees out of phase results from the receiver. Okay. Loving that it's stuck. And okay, here's another one for you. So if you had put this x2 here, you would have another result. So when the transmitter phase is 0, basically it's a sine, then the receiver is at 270 degrees out of phase there. It's not 360, it's 270. I think that's the number there. So it's basically has a different phase shift altogether. And so when the pressure at the receiver or the transmitter is 0, the pressure at the x2 is negative. So this is 0, this is negative. So that's how you can kind of correlate. So the pressure, so depending on where that transmitter is, and if you have a high frequency, like you just change the I forget what the wavelength in air would be at 40 kilohertz, but if you just start to change this transmitter or receiver, then you'll just be changing the phase back and forth. Now the amplitude will also change because the acoustic power is diluted as when you keep going outward away from your transducer. However, your phase will also be changing as you move positions. So it begs the question, like, should we put the transmitter? Let's say you're trying to optimize power or something. Should you put the transmitter or the receiver such that such that the phase of the receiver is the same as the phase of a transmitter? Is that significant? The answer is no. This is not a resonating system. Your transmitter and receiver are not in resonance with each other. They're not bouncing sound back and forth between each other. They may be resonating independently of each other, but they're not resonating together as a system. All right? So what's the significant of phase here? It's nothing. Only placement. That's the only thing that has to do with phase. So this is not a resonating system altogether. They're not the sound waves bouncing off the transmitter is not going, bouncing off the receiver from the transmitter, not going back to the transmitter, then it's going back to the receiver. That's not what's happening, because there's so much diluted energy in the air that you can't resonate such a system. The energy is just being lost in droves. So it's not a Q factor that you can kind of optimize for. You lose so much energy in that transfer. But if you had a closed system, you may be able to actually stimulate a resonance if you did have sufficient acoustic waves going back and forth, but they're fairly low energy in comparison to the elastic energy of the transducers. And that ends this video. So you've been watching episode, I think, 37. Your host, Dr. Shikani, answer your questions. This was a question posed to me, sent through email or actually text message. Not everybody jump on that, please. But you can check the link for the descriptions. I'll have the notes here uploaded pretty soon. There's a link to sign up for my email list. You can receive these updates for my videos there, and as well as the presentation notes too. How convenient. And also you can take a look at my consulting services and offerings for ultrasonic transducer consulting that I do as part of my company, Ultrasonic Advisors. So I will see you in the next video, number 38. Maybe it'll be your question if you ask. Thank you.